Welcome back to Lesson 3 in our course Fundamentals of Operating Systems, based on the textbook Operating System Concepts, 10th edition, by Abraham Silberschatz, Greg Gagne, and Peter Galvin, published by Wiley Publishing. In this lesson, we are going to start our investigation of the various scheduling algorithms for the CPU. And we'll begin with first come, first serve. I think what we'll do is actually create a separate video lecture for each one of the different scheduling algorithms. So that should make them very short and quick and easy to follow. CPU scheduling deals with the problem of deciding which of the processes in the ready queue is to be allocated the CPU's core. By far, the simplest scheduling algorithm is first come, first serve. With this scheme, the process that requests a CPU first is allocated to CPU first. The implementation of first come, first serve policy is easily managed with a first in, first out queue. When a process enters the ready queue, its process control block is linked onto the tail of the queue. When the CPU is free, it is allocated to the process at the head of the queue. The running process is then removed from the queue. The code for first come, first serve scheduling is simple to write and to understand. On the negative side, the average waiting time under first come, first serve is often quite long. Consider the set of processes in this slide that arrive at time 0 with the length of the CPU burst given in milliseconds. If the processes arrive in the order P1, P2, P3 and are served in a first come, first served basis, we get the results shown in the Gantt chart, which is a bar chart that illustrates a schedule, including the start and finish times of each of the participating processes. The waiting time is 0 milliseconds for process 1, 24 milliseconds for process 2, 27 milliseconds for process 3, and therefore the average is 0 plus 27 plus 23 divided by 3, or 17 milliseconds. Doesn't that look like that processor hog I talked about a while ago? If the processes arrive in P2, P3, and P1 order, the results will be as shown in this Gantt chart. The average waiting time is now 6 plus 0 plus 3, or 3 milliseconds. This reduction is substantial. Therefore, the average waiting time under first come, first serve is generally not minimal and may vary substantially if the process's CPU burst times vary a lot. In addition, consider the performance of first come, first serve scheduling in a dynamic situation. Assume we have one CPU bound process and many input-output bound processes. As the processes flow around the system, the following scenario may result. The CPU bound process will get and hold the CPU. During this time, all the other processes will finish their input-output and will move to the ready queue waiting for the CPU. While the processes wait in the ready queue, the I/O devices are idle. Eventually, the CPU-bound process finishes its CPU burst and moves to an input-output device. All the I/O-bound processes which have short CPU bursts execute quickly and move back to the input-output queues. At this point, the CPU sits idle. The CPU-bound process will then move back to the ready queue and be allocated the CPU. Again, all the input-output processes end up waiting in the ready queue until the CPU-bound process is done. This effect results in lower CPU and device utilization than might be possible if the shorter processes could go first. Note also that first come, first served scheduling algorithm is non-preemptive. Once the CPU has been allocated to process, that process keeps the CPU until it releases the CPU, either by terminating or by requesting an I/O. The first come, first served algorithm is particularly troublesome for interactive systems, where it's important that each process get a share of the CPU at regular intervals. It would be disastrous to allow one process to keep the CPU for an extended period. Okay, that concludes our discussion of first come, first serve. Next, we will move to the shortest job next algorithm. So let's take a break here. As soon as you can, come on back and we can begin to study shortest job next.